Dear students, I would like to talk about the highway drainage, which is the module 5 in VTU CBCS syllabus, and the subject code is 17CV 63. First, introduction to highway drainage. Highway drainage is the process of removing and controlling excess surface and subsoil water within the right of way. During rains, part of the rainwater flows on the surface and part of it percolates through the soil mass as gravitational water until it reaches the groundwater table. Removal and diversion of surface water from the roadway and adjoining land is termed as surface drainage. Diversion or removal of excess soil water from the subgrade is called subsurface drainage. Then, what is the importance of highway drainage? The significance of drainage. The increase in the moisture content causes decrease in strength or stability of a soil mass. The variation in soil strength with moisture content also depends on the soil type. Highway drainage is important because of the following. The increase in moisture content causes decrease in strength or stability of a soil mass. The variation in soil with moisture content also depends on the soil type. Highway drainage is important because of the following. Excess moisture in soil subgrade causes considerable lowering of its stability. Increase in moisture causes reduction in strength of many pavement materials like stabilized soil and waterborne macadam. In some clay soils, variation in moisture content causes considerable variation in the volume of the subgrade. This may lead to the pavement failure. Because of poor drainage, formation of waves and corrugations may lead to flexible pavement failure. Sustained contact of water with bituminous pavement causes stripping of bitumen from the aggregates. The prime cause of failure of rigid pavements is due to mud piping. Excess moisture causes increase in weight and thus increase in stress and simultaneous reduction in strength of soil mass. This is one of the main reasons of the failure of earth slopes and embankment foundations. Erosion of soil from top of an unsurfaced roads and slopes of embankment, cut and side hillside is also due to surface water. The surface water is to be collected and then disposed of. The water is collected first into longitudinal drains and then the water is disposed of at the nearest stream, valley or to any of the water courses. Collection of surface water. The water from the pavement surface is removed by providing camber or cross slope to the pavement. The rate of cross slope is decided based upon the type of pavement and amount of rainfall. In rural highways, the water drained off from the pavement surface is led to the side drains. The side drains of rural roads will be generally open drains of trapezoidal shape, and these drains are provided parallel to the road alignment and are called longitudinal drains. But in urban areas, covered drain trenches are used. In urban roads, because of the land width and also due to the presence of footpath, dividing islands, and other road facilities, it is necessary to provide underground longitudinal drains. Water drained from the pavement surface can be carried forward in the longitudinal direction between the curb and pavement for short distances. This water may be collected in catch pits at suitable intervals and led through underground drainage pipes. A grating is provided to prevent the entry of rubbish into the drainage system. The following figure explains how the collection of surface water and led into the drain is shown. Design of subsurface drainage system. The design of subsurface the system may be divided into two phases: hydrologic analysis and hydraulic analysis. Hydrologic analysis. The main objective of hydrologic analysis is to estimate the maximum quantity of water expected to reach the element of the drainage system under consideration. A portion of precipitation during the rainfall infiltrates into the ground as groundwater and a small portion gets evaporated. The following rational formula is used to estimate the peak runoff water from highway drainage and is given by Q is equal to C into I into AD, where Q is equal to runoff in meter cube per second, C is equal to runoff coefficient expressed as the ratio of runoff to the rate of rainfall, I is equal to intensity of rainfall in millimeter per second, and AD is the drainage area in 1000 meter squares. The above expression is not dimensionally balanced. The value of runoff coefficient C depends mainly on the type of surface and slope. The value of C may be taken as 0.8 to 0.9 for bituminous and cement concrete pavements, 0.35 to 0.7 for gravel and WBM pavements, 0.4 to 0.65 for impervious soil, 0.3 to 0.55 for soil covered with turf, and 0.05 to 0.3 for pervious soils. When the drainage area consists of several types of surfaces with runoff coefficients C1, C2, C3, etc., with their respective areas A1, A2, A3, etc., the weighted value of runoff coefficient is determined from C is equal to C1A1 plus C2A2 plus C3A3 whole divided by A1 plus A2 plus A3. The design value of rainfall intensity I is to be determined for the expected duration of storm and frequency of occurrence. The time for water to flow through the drain between the inlet and the outlet points is determined based on the allowable velocity of flow in the drain, generally ranging from 0.3 to 1.5 meter per second. The frequency of occurrence of storm or the return period may be taken as 5, 10, or 25 years. From chart of typical rainfall intensity duration curve, that is, it is represented in figure 11.4, page 522 of Chestnut Khanna. The design value of the rainfall intensity I is found corresponding to the duration of storm and selected value of frequency, that is represented in the charts 11.3 and 11.4. The drainage area is computed from a contour map. This area is expressed in units of 1000 meter squares to obtain the value of AD. Thus, the estimated value of C, I, and AD, the design value of Q for the longitudinal side drain, is obtained. Hydraulic design. Once the design run of Q is determined, the hydraulic design is to be carried out. If Q is the quantity of surface water in cubic meter per second, which is to be removed by a side drain, and V is the allowable velocity of flow in meter per second, the area of drain in meter squares is found from Q is equal to AV. That's a continuity equation. The velocity of unlined channel must be high enough to prevent silting and should not be too high as to cause erosion. The allowable velocity of flow depends on the soil type. For sand and silt, it is 0.3 to zero point 0.5 meter per second, loam 0.6 to zero point 0.9 meter per second, clay 0.9 to 1.5 meter per second, gravel 1.2 to 1.5 meter per second. For good soil covered with well-established grass, it is taken as 1.5 to 1.8 meter per second. For computing velocity of flow, Manning's formula is used, which runs as V is equal to R to the power of 2/3 and S to the power of half, where V is equal to average velocity in where V is equal to average velocity in meter per second, N is the Manning's roughness coefficient, and R is the hydraulic mean depth. The roughness coefficient values depend on the type of soil in unlined channels. For ordinary earth, N is equal to 0.02. Earth with heavy vegetation or grass, N is equal to 0.05 to zero point 0.1. Concrete lining, the value of N is 0.013. For rubble masonry, N is equal to 0.04. The slope of the longitudinal drain of a known or assumed cross section and depth of flow may be determined from Manning's formula for the design values of flow V, roughness coefficient N, and hydraulic mean depth or hydraulic mean radius R. What are the design steps that are to be carried out? The first one, the frequency of return periods such as 10 years, 25 years, etc. is decided based on the finance available. The values of coefficient of runoff C1, C2, C3, etc. from drainage areas A1, A2, A3, etc. are found and weighed value of C is computed. The inlet time T1 for the flow of storm water from the farthest point in the drainage area to the drain inlet along the steepest path of flow is estimated from the distance, slope of the ground, and type of cover. For this purpose, charts 11.3 and 11.4 of Chisholm-Khanna may be used. The time of flow along the longitudinal drain in T2 time is determined for the estimated length of the longitudinal drain L up to the nearest water course, and allowable velocity of flow V in the drain is then T2, that's the time, is equal to L divided by V. The total time T for the inlet flow along the drain is taken as the time of concentration or the design value of rainfall duration T, that is given by T1 plus T2. Next, from the rainfall intensity duration curves, that is the figure chart or the figure 11.4, the rainfall intensity I is found in millimeter per second, corresponding to duration T and frequency of 10 period. Next, the total area of drainage area is found in 1000 meter squares units. The runoff quantity Q is computed from Q is equal to C into I into AD. The cross-sectional area of flow A of the drain is calculated from A is equal to Q by V, where V is the allowable speed of flow in the drain. The required depth of flow in the drain is calculated for a convenient bottom width and side slope of the drain. The actual depth of open channel drain may be increased slightly to give a freeboard. The hydraulic mean depth R is calculated. The required longitudinal slope S of the drain is calculated by using Manning's formula, adopting a suitable value of roughness coefficient N. Now we shall be able to solve a simple problem on the surface or drainage system design. The maximum quantity of water expected in one of the open longitudinal drains on clayey soil is 0.9 cubic meter per second. The design, the cross section and longitudinal slope of trapezoidal drain, assuming the bottom width of the trapezoidal section to be 1 meter and the cross slope to be 1 to 1.5 horizontal. The allowable velocity of flow in the storm is 1.2 meter per second and Manning's coefficient N is equal to 0.02. Now we shall come to the solution. First, cross section of the drain. The allowable velocity of flow through the clayey soil is given as 1.2 meter per second. Number 1, cross-sectional area of drain A is equal to Q by V, that is 0.9 by 1.2, that is 0.75 meter squares. Second one, cross-sectional area A is equal to B plus ND into D, that is equal to 1 plus 1.5 into D, 0.75 meter squares. Solving for D, the above equation, we get D as 0.450 meter. Next one, fourth step. There is actual depth of flow for the design quantity of water through the trapezoidal section. Hence, allowing a freeboard of 0.15 meter, the depth of the side drain may be taken as 0.45 plus 0.15, that's equal to 0.60 meter. Next, we shall design the longitudinal slope S. So we have V is equal to 1 by N into R to the power of 2/3 and S to the power of half. Here, the N value is 0.02 and V is 1.2 meter per second. The wetted perimeter is given by the equation P is equal to square root of D square plus D square multiplied by 2 plus 1. So, substituting the values of the quantities, we get the wetted perimeter as 2.62 meter. Then hydraulic mean radius or hydraulic mean depth is given by the equation R is equal to A divided by P. So this 0.75 divided by 2.62 gives 0.286 meters. Then S to the power of half is equal to Vn divided by R to the power of 2/3. That is 1.2 into 0.02 divided by 0.286 to the power of 2 thirds. That gives 0.0553, that is expressed as 1 in 320. Hence, we shall provide a longitudinal slope of 1 in 320. Next, we shall be able to solve a second problem on this. The distance between the farthest point in the turf covered drainage area with an average slope of 1.5% towards the drain and the point of entry to the side drain is 200 meters. The weighted average value of the runoff coefficient is 0.25. The length of the longitudinal open drain in a sandy soil from the inlet point to the cross drainage is 540 meters. The velocity of flow in the side drain may be assumed as 0.6 meter per second so that the silting and erosion are prevented. Estimate the design quantity of flow on the side of the drain for the 10 years period of frequency of occurrence of the storm. Now, we have C is equal to 0.25. By graph 11.3 of Gestone Canal, the inlet time T1 for average turf with 1.5% slope corresponding to 200 meters is 33 minutes. It is worked out by interpolation. The time T2 for water to flow through 540-meter length of drain at 0.6 meter per second, that is T2 is equal to 540 divided by 0.6 into 60 gives 15 minutes. Therefore, the duration of time of concentration T is equal to T1 plus T2, that is 33 plus 15, 48 minutes. Therefore, the drainage area is 540 into 200, that gives 1 lakh 8,000 meter squares. Then this should be expressed in 1000 meter squares units. Therefore, AD is equal to 108,000 divided by 1000 gives 108. The design value of runoff rainfall intensity for 10 years of frequency of occurrence and corresponding 48 minutes duration is equal to 70 mm per hour by the chart 11.4. Then I is equal to 70 divided by 3600, that is 0.019 millimeter per second. Q is equal to Z into I into AD, 0.25 into 0.019 into 108 gives 0.525 cubic meter per second.